We are going to start the lecture on nanotechnology and chemical engineering. So we have already prepared different nanomaterials, nanoscales materials, nanoparticles, and carbon nanotubes, carbon-based materials. So fullerenes, many materials we have prepared. So now we have started analysis of that material. So today we will discuss about BT surface area analysis of that material. So once let's say here is one image, you can see that materials in the forms of powders that we can prepare, that is the nanomaterials. So that nanomaterials may be CNT, graphene, activated carbons, or any metal oxides. So these materials not uniform, the dimensions is very small. So as a result, the surface area of this type of materials or pores develops inside of that materials. That is very important for a specific application. So inside if you look very closely, so different type of shapes of that metals, metal oxide, metal sulfide, whatever the materials that we have taken, so that may be distributed or arranged different way, means cylindrical shape, spherical shape, or cubical shape. So different way the arrangements is there. So if you look very closely, so in that particular materials many type of pores are present. So here we can see the materials, many pores are present. That pores we can classify micropores, mesopores, or macropores. So here is the structure. So depending upon the dimension of the pores, we can classify that whether it is micropores, that is less than 2 nanometers. If it is 2 to 50 nanometers, then we can say it is mesopores, and if it is more than that, so 50 nanometers, 100 nanometers, 80 nanometers, we can say mesopores. So all these three type of pores present in a particular materials, or maybe micropores only presents, or maybe mesopores presents, micropore presents, or few materials maybe macropores are present. So depending upon the materials that we have prepared, so different type of pores formations are there. So once we prepared some materials having very particle size, large particle size, that is micrometer range, the materials we have prepared, very large particle size. So then surface area would be very low, or if its dimension is like that, so surface area would be this. If we decrease the particles into nanoscales, so means centimeter to mm to nanometers, so then the surface area gradually increase. From here the surface area was very low, and here extremely high surface area we can get. So once that materials changes from micrometer or meter to nanometer range, so then surface area would of course will gradually increase. So here's the BET surface area analysis, that is the method or technique is available, so that we can use to analyze the BET surface area of that specific surface area of that materials, if it is porous materials, and also its pore size, and pores, total pores, pore volumes we can measure with the help of this analysis. So that will study basically actually when we prepares in a particular catalyst or materials, any metal oxides, so that is used many applications. So depending upon their property, if you are able to increase the surface area, increase the pore, so then materials will be, let's say wastewater treatments also, then the materials will be much more better than having less or less surface area, less pores. Okay, so therefore this property is very important, so we can measure. So here one example, catalyst having high surface area leads to higher catalytic activity as compared to the catalyst having less surface area. So in this particular BET, so specific surface area analysis, so in this particular way analysis techniques, we can get specific surface area, average pore volumes, and pore size, means through these experiments. Here the theory little bit will discuss, and how does it work the system. So in particulars, I said solid materials we have taken. So here's nitrogens, that would be as a pro molecules, so that would be adsorbs over the surface of that powder sample, that or porous material that we have taken at very low temperatures. Okay, so then amount of the nitrogen molecules that is get adsorbs at different partial pressures we will maintain, or pulse chemabsorptions, nitrogen molecules will be placed in that vacuum chambers where materials will be placed. So after that amount of the materials get adsorbed, nitrogen get adsorbed of the surface of the materials that we can get, or we can the volumes amount of the materials get adsorbed, that we can quantify, that we can note down in a particular means programs is theirs with that means the systems or apparatus that is individual points we can get. Okay, so if we increase the partial pressures or that nitrogen, that would get adsorbed from the surface of the material. Since at low partial pressures, low amount of the materials or nitrogen should be there, the adsorption should be very low. If we gradually increase the quantity or partial pressure of the nitrogens at the temperatures, low temperatures, though then quantity of that nitrogen gas or molecules that would get adsorbed with increase, increasing partial pressure, that would gradually increase. Okay, so once we relieve the pressures or decrease the pressure or partial pressures, means once gets adsorbed of that materials, this is our catalyst or surface solid oxides. Here's nitrogen molecules get adsorbed. If we increase the pressures and once dissolves or relieve the pressures, that molecules will leave the from the surface. So here's x-axis, you can see that relative partial pressures. So we have started at low partial pressure to high partial pressures. So here's red one, that curves, that is the adjacent isotherms that would gives, means if we increase that partial pressures of nitrogens at low 77 Kelvin, that nitrogen molecules get adsorbed over the surface, and after that if we dissolves or relieve the pressures, so then nitrogen molecules whatever that would adsorb over the surface, that would come out, and that this type of isotherms, desorption isotherms we can get. So once we have to go from this to this, we'll get red isotherm, that is isotherms, and once we decrease the partial pressures, so then the amount of get adsorbed would be dissolved. So both isotherms we can get, and based on that we can analyze the type of materials we have prepared, what type the porosity. So here this is the BET equations is there, this is called isotherms. Okay, so adjacent desorption isotherms, and this is the BET equation that theory was developed, and that we'll discuss details. So before that, about that instruments, so here is the BET experimental setups or instrumental setups. Here is this, and few gas cylinders we need to, means here's pure nitrogen gas cylinder is required, and 30.2% volume percent of nitrogen, balanced helium for specific surface area analysis, and nitrogens, and 5% helium that we have to use for measurements of the pore volumes. So here's the basics, how does it look like the system. So here's you can see a chambers or gas tube is there, quartz tube, where catalyst or porous materials we can place here, porous materials we can place over there. After that we can heat up that materials at 200-300 degrees centigrade. So here step by step process are there. So we need to degassing some of the materials for 2 to 6 hours to remove if there is any adjunct moistures, any organic volatile materials is present, we have to remove that. And after that we keep means cool down the samples into 200 room temperatures, and then at liquid temperatures or liquid nitrogen temperature 77 Kelvin, we have to reach that temperature by using liquid nitrogen bath. Here's liquid nitrogen should be that. So at the temperature sample should be that, and after that we can pass the nitrogens, and then nitrogen would be adsorbed at the temperatures, gas would be adsorbed over the sample surface, and partial pressure or relative pressures we can increase. The rest of the, means the amount of the nitrogen would be adsorbed over the surface. So after that rest would be whatever the material nitrogen's gas that does not absorb over the surface will be passed out, and after that the quantity we can measure the how much quantity of the nitrogen gets adsorbed over the surface of that materials, porous materials. So this type of isotherms will comes. So in pore size and pore volumes, Barrett, Joyners and Halenda methods is there for pore size and pore volumes analysis. So here's, means here is the pore volumes if you want to get, so then volumes get adsorbs that we have to quantify with the help of instruments. And if you know the molar volumes of that liquid nitrogen at the temperatures that is fixed for that particular liquid nitrogens, so then average pore volumes of that materials we can measure. And then if we want to get average pore size, so average pore size or pore radius, means I said micropores, mesopores or macropores are present in that mesoporous materials. So that's if we are able to know the average pore volumes, and then specific surface area of that materials. So pores radius we can calculate by using this, or also using Kelvin equations by using relative pressures. This is the relative pressure of nitrogen, P by P0 if you know, and Vms, that is the molar volumes liquids nitrogens at that 77 kelvins we know, and other parameters RT, this RPT we can calculate. Using these equations also we can measure the average pore radius or pore size of that pore presents in that particular samples or the porous materials. Okay. And in case of the BT experiment I said, so nitrogen millimeter per mercury, that is the partial pressures. So this is 10, 20 up to 500. So we can maintain when absorptions will be there. So we can increase graduals the partial pressures, and if we increase the partial pressures, so then volume of the gas or nitrogen that is being adsorbed over the surface, that also gradually increase. Okay. If we increase the pressure or partial pressures, so then amount of the gas would gradually increase. So from there P naught by P or relative pressures we can measure. Okay. So using these equations, so Vm, that is the monolayer coverage, means when a surface is there, so once layers, that is the pores presents, so how many molecules that would get adjust to complete cover, so that is called monolayer coverage. So that we can find out, and using these equations we can, Vm is the monolayer volume, so amount of nitrogen gas is required to cover that surface, means let's say this is our surface. So if we want to cover, this is called monolayers. This is the complete coverage of that surface. The amount of gas is required, that is Vm. Okay. So that we can calculate with the help of these equations, and using this equation the surface area we can means get with the help of that equation. So that we will discuss later. So usually any porous materials, for examples here I am showing, let's say materials having 200 meter square per gram and average pore size 11 nanometers for examples, and let's say this is L2O3 nanomaterials we have prepared. So it's having 200 meter square per gram surface area, average pore size that is 11 nanometers, and pore volumes that is expressed in terms of 0.52 centimeter cube per grams. So here per gram basis of the samples, means for the analysis we have to use some quantity of the samples. Here we have taken, let's say 100 gram of the solid samples. So we have taken, and the results we are getting here. Okay. So here there are many applications I said. So these methods we can use to find out the specific surface area, pore size and pore volume. So depending upon that materials, the surface area are different. One materials to another material, the specific surface area or BT surface area are different. Pore volume also depending upon the nature of the materials, pore size and pore volumes also would be different. Few materials having extremely low surface area, few materials having extremely high surface area. So if you are able to prepare so that materials having extremely high surface area, highly porous or pore size are present, so then that would help us to get the specific means property of that particular materials. Okay. So that would assist either good means a good catalyst or good means wastewater treatments or any mass transfer properties or any other properties, so that we are looking for, so that we can easily get. Okay. So here's the surface, here's that materials I said, the here's the means this is our materials, and this is let's say nitrogen molecules. So that may get adsorbs over the surface. Physiabsorptions means adsorptions may be physiabsorptions or maybe chemiabsorptions. If physiabsorptions, that molecules may come over the surface and just attached with the help of van der Waals force of attraction. So here is this adsorptions is there, so there is no bond formations, but in case of the chemiabsorptions with the surface there is some bond formations is there. So this is called chemiabsorption, this is called physiabsorption. So each particular adsorption process both are exothermic, but energies are different. So in case of physiabsorptions, I said van der Waals force of attractions is there in both molecules and atoms, so energy is very low, and in this case heat of adsorptions is relatively higher. So here the theory, so before come to the BET theory, Bronner, Emmett and Taylor, so they have developed this based on multi-layers physical adsorptions of that nitrogen molecules. So before that, this is the theory widely accepted. So before that, Langmuir theory, Freundlich and Temkin, so they have also means developed some mathematical equations, and based on there are some assumptions. So that theory and the surface area analysis that was means proposed. Okay, so this is the latest means initially means BET theory that has come based on Langmuir theory. So each theory has some means limitations, means Langmuir, Freundlich and Temkin. So based on their assumptions, this type of equations they have developed, and these equations is based on multi-layer adsorptions is means widely it's good fitted with the experimental observations. Okay, so here's in Langmuir isotherms, I said they're based on monolayer coverage, this theory. So here's this is the nitrogen molecules that is covered completely one monolayers or single layers of nitrogen that is get adsorbed. So here you can see this is multi layers. Okay, so means initial first layer is with that surface of that materials or the samples with that nitrogen molecules first layers, and after that second, third, fourth layers, so that is not with the means materials or nanomaterials or particles or catalyst whatever we have taken. So rest is with that next layers onwards, that is not directly with that samples or catalyst or metal oxide whatever. So here this is physics options, and this theory means Langmuir theory that is based on chemistry options, and BET theory that is physics options and multi-layer adsorptions. This is monolayer adsorptions and this is multi-layer adsorptions. Okay, so based on that both the theory were developed. So here's so in case of the Langmuir isotherms or Langmuir's theory or this equations was developed. So here's this you can see the nitrogen get adsorbs, formations of monolayers when there is adsorptions, when it is desorptions pressure is low, so then whatever the molecules adsorbs that is come out from the surface. So here's this is multi-layers of nitrogens at 77 kelvins, that is get adsorbs, formation of multi-layers. When it is dissolves this way, the molecules will come out from the surface. Okay, so here's multi-layer physics options based on BET theory. Okay, BET theory, and here's Langmuir theory based on physics options as well as chemistry options. So monolayer coverage or single layer coverage. Okay, so depending upon that means when that molecules get adsorbed experimentally and theoretically both may be are different. Okay, so there are some other theories also I said, Freundlich and Temkin isotherms. So these are the isotherms equations were used, and so this theory was based on chemistry options and physics options at low coverage, means here greater than once, and in case of the Temkins that is the chemistry options based on chemistry options. Okay, so here's the isotherms means initially I said Langmuir isotherms. The isotherms, the volumes of that nitrogen get adjusted over the surface by increasing pressures of that during adsorptions. So it is looks like this and gradually increase. Okay, so if we increase the pressures, the amount of the gas that is adsorbs it would follow like that. After that saturations will come, so that is plateau we can say. So that is in case of the Langmuir isotherms and Temkin isotherms, both is following like this way. Okay, but when in case of the Freundlich isotherms, so if we increase the pressures, the volumes get adsorbs, that will gradually increase, and after that exponentially also increase instead of getting any plateau. Okay, so this is the basic difference in between these two, the three, and after that the BET theory or BET isotherms I said. So in this case also similarly, if we increase the partial pressures or pressures of that nitrogens, the volumes get adsorbed. It is started with like this, it is gives some plateau, and after that further if we increase the pressure, the nitrogen molecules get adsorbed and multiple layers or multi-layer physics options is there. So here the fractions coverage of the surface, the blue is the pores and red is the nitrogen molecules, and blue is the samples pores, you can say pores of catalyst or samples. Okay, so nitrogens here the fractions coverage is 0 to 1, not fully coverage. So in this case of in surface coverage in this case, and so in Langmuir and Temkins here monolayers complete monolayer formations is there, you can see. So up to this plateau or monolayer formations is there. And in case of the BET isotherms, not only monolayers, up to this monolayer formations is there. And after that, if we increase the pressures, so theta greater than 1, see here theta equals to 1 and here theta greater than 1. So multi-layer formation, these are the layers, other layers formations is there. So here that is actually means theory and experimentally how does it look like, means the when nitrogen molecules come over the surface of the pores or the catalyst surface or material surface. So different type of adsorptions, so formations is there, means molecules get adsorbed by formation of monolayers, complete monolayers or incomplete monolayers or maybe multi-layer formations. So now we have different type of materials, different type of porous materials, nanoporous materials, pores or nanopores materials we have. So once we want to get that surface area or isotherms for that particular materials, whatever we have prepared, we want to characterize. So different type of isotherms may forms. So here type 1, type 2, type 3, type 4, type 5, type 6. So depending upon the materials we have prepared, different type of isotherms it may forms. Okay. So here also both adsorption desorption curves are there. Here is also adsorption desorption curves are there. Here is also there. Here is also there. So here is also adsorptions and desorptions curves both are present. Isotherms both are present. Here is also present. Here is also red and blue curves you can see. So depending upon nature of the materials, different type of natures or surface isotherms we can get. Okay. So blue one is the adsorptions, red one is the desorptions isotherms. So it indicate actually the amount of gas adsorbs, amount of gas dissolved during adsorption desorption process. Okay, of adsorption desorptions of nitrogens. So here in this type of isotherms, actually micropores, narrow micropores are present. So here's sudden jumps and then plateau formations is there. Here's means little gradually increase concave types and then saturated. Here is shaped type of isotherms is present. Here micropores will be filled and then saturation is comes and then multi-layer formations is there. Here concave downwards. Okay. So means or convex downwards. So in this case means in this type of surface. So convex down weak substrates means depending upon their natures of isotherms, it also indicates the type of materials that we have prepared. Okay. So here's weak substrates. So no clear monolayers or weak interactions at you can say. Okay, so in case of the type 4s, mesoporous type of materials formations is there. Here's hysteresis loops is there. This is called hysteresis loops. Okay, so hysteresis loops formations is there and monolayer, multilayer adsorptions and capillary condensations both are present. Means monolayer coverage in the micropores at this particular point and this monolayer formations, this is multilayer formations, this is capillary condensation. So that way means if we increase the partial pressures of nitrogens at 77 kelvins over the surface of the materials, so means one stage to the another stage, another points, so different pores will be filled with that materials. Okay, in this case there is no hysteresis loops. In this case hysteresis loops is there. In case of the type 5 S-shaped isotherms forms, here this is S-shaped isotherms, but here poorly developed micropores with mesopores. Okay, so in this type of materials, and here you can see zigzag type of isotherms which comes. So here's the adsorptions of that nitrogens over the surface of the materials is steps, means here's non-porous materials with uniform surface. So here means sometimes pores are blocked with some others elements. So you have to pressurize, then some gases would be get adsorbed and means non-uniform and here stepwise adsorption is there. Okay. So here's type 2 and type 4 isotherms both are side by side we have placed. You can see here's no hysteresis loops, here hysteresis loops are present. Okay. So here's first type 2 type isotherms. You can see if we started from here to here means low pressure to high pressures we are going, means nitrogen pressures and volumes of the gas that is get adsorbed. So here's at this particular points micropores are present over the surface. In a surface or the suppose porous materials you have taken, it consists three different type of pores: micropores, mesopores, macropores. So initially micropores will be filled with this, and this is unsaturated bindings. So here's not complete. So when it is come here, monolayer coverage is there, saturated monolayer bindings, and after that you can see multilayer formations is there, and after that I said phase separations or completely pores completely filled. See here, this is actually pores of that materials. This is pores. This pore is filled with all liquids and nitrogen that is converted into liquid stage, or you can say phase separation. Initially that was in gas, and after that increase the pressures, so it would pore will be filled, and capillary condensations you can say at this stage actually. Okay, so this is okay. So this is called capillary condensations. Okay, so liquid like states you can say. So this is mesopores completely fills full hysteresis curves. Okay, at this particular point. Here's this type of H type or hysteresis loops that indicates mesopores are present, and this type of concave upwards that indicates micropores are fillings. Okay, so this pore structures, so type 4 and type 4 materials, hysteresis loops also different types. Okay, so hysteresis loops type A, type B, type C, type D, different type of hysteresis loops present. So pores may be different types, cylindricals, these plate types or these types or bottles type. So depending upon their different type of nature of pores that is present, mesopores. So type of isotherms we can see, and based on that we can say which type of pore structure that is present in that mesoporous materials. Okay, so it is given here, so details you can see. Okay, so here's a table was showing, so we have different type of activated carbon, silica, alumina, zeolites, clay, raw biochars, activated biochars, CNT, graphene oxides, MOF type of materials, different type of materials that we can prepare by following the particular method of synthesis. Once we analyze the specific surface area of these materials, you can see depending upon that material the surface area is extremely low and extremely high. So MOF materials having extremely high surface area, and this metal oxide or ceramic type of oxides or this having very low surface area. Okay, here some MOF materials also was taken, so here you can see extremely high surface area. So here also few examples are showing. So cobalt MOF, manganese MOF was taken. So here type 2 isotherms, and this is showing type 4 isotherms, this is type 3 isotherms, this is type 4 isotherms. Okay, even pore size also here's 2 to 6, 2 to 5 nanometers, 2 to 5 nanometers within that range. This cobalt MOF and these manganese MOFs having surface area pore size that is distributed, so within 0 to 10 nanometers or 15 nanometers within that. Okay, this is MOF, manganese MOF, this is cobalt MOF. So pore size also are different. Okay, so here's different type of isotherms you can see. So first one is nickel MgO, second one is lanthanum MgO. There is no hysteresis loops is present, but when nickel MgO over alumina, so then hysteresis loops is present. When lanthanum MgO, okay, this sample is different, lanthanum, nickel lanthanum MgO alumina. So here also hysteresis loops are present. Okay, so here's you can see the micropores concave upwards, so micropores are filled in this case. You can see here is also micropores are fillings, and some then intermediate plateau regions is there, monolayer coverage, and then high pressure convex downward you can see, and then finally multilayer formations is there at this particular points or in this particular points. Okay, so thank you. So today is up to this. So today we discuss different types of the materials, so that we have having a different type of pores: micropores, mesopores or macropores. So that pores assist means once we synthesize or follow a particular method of synthesis, so then we can get a particular or specific type of pores we can develop, so that will enhance the catalytic activity, means material property, wastewater treatments, heat transfer, mass transfer properties, that would increase or change. Even that materials having many applications, CO2 absorptions or wastewater treatment, many applications. So if we are able to develop the materials having extremely high surface area, then we can get good property of that particular material. So if we want to know whether that specific method on the materials is good or not, so then we have to do the specific surface area we have to analyze or we have to measure, that is liquid nitrogen absorption methods or nitrogen gas absorption method. We can find out the specific surface area as well as pore size, pore volumes that we can measure with this method. So BT specific surface area is very important. So with that, other different theories are also there, so that also we have discussed or compared different type of isotherms. Okay, so that is very important study. So today is up to this. Thank you.